The U.S. Department of Energy has assembled a team of researchers to investigate what it would take to build a one-of-a-kind test reactor to support research, development, and deployment of the next generation of nuclear technologies. DOE proposed building the versatile test reactor following several studies that analyzed the need for a fast-spectrum reactor that could test materials, fuels, and other components at higher neutron energies and fluxes than what is currently available. The VTR team, which includes 6 national laboratories and multiple universities and industry partners, is working to develop a conceptual design, cost and schedule estimate, and other elements necessary for DOE to decide whether to proceed with the project. The team has made significant progress on a proposed design, which is necessary for building as accurate a cost estimate as possible. The proposed VTR design is based on a mature sodium-cooled fast reactor, or SFR, technology, developed by industry and informed by many years of operating experience and knowledge. This proposed approach would provide a reliable test facility with versatile operational capabilities and maximum mission flexibility. Research materials would be transported into the reactor building through a truck lock into an area called the experiment hall and then removed by an overhead crane. The material would either be stored or immediately configured into experiment assemblies, which are later inserted into the reactor. The experiment hall has dedicated areas for experiment assembly and disassembly and is also used for transferring experiments and driver fuel into or out of the reactor or storage locations. The VTR takes advantage of design features that provide enhanced safety performance. The design incorporates 3 main safety criteria, which are, first, controlling the reactor power and reactivity; second, ensuring adequate cooling for both operating and shutdown conditions; and third, ensuring proper confinement of radioactive materials. The next level down is a view of the top of the reactor, or reactor head, along with the drivers for the control rods, the fuel transfer port, which is the mechanism for inserting fuel into and removing fuel from the reactor, as well as dedicated insertion points for instrumented experiments. VTR reactivity and power levels are regulated using control rods with a neutron absorber, boron, to adjust the rate of the nuclear reaction and compensate for fuel consumption. Withdrawing the control rods from the core causes an increase in power, while inserting them decreases power or shuts the reactor down completely. These controls are similar to accelerating and braking a vehicle. This safe and effective process is utilized in all existing U.S. commercial reactors. Specific design of the fuel and supporting structures in a sodium fast reactor provide an additional layer of defense by ensuring that power will decrease if abnormal events such as loss of flow or loss of heat sink cause an unexpected temperature increase within the reactor core. The fuel to power the VTR is metallic alloy, which provides superior heat transfer into the sodium reactor coolant. VTR operates at much lower pressures, essentially atmospheric pressure, than the light water reactor designs used in existing U.S. nuclear reactors. Cooling the VTR could be compared to the way a car radiator operates, but with one important difference. Where a car radiator circulates coolant outside of the engine, the VTR design does not circulate the primary coolant outside the reactor vessel. Instead, reactor heat produced by normal reactor operation is removed through a secondary loop that rejects heat into the atmosphere through large sodium-to-air heat exchangers. The low coolant pressure and the confinement of the primary coolant inside the reactor vessel provides added safety by reducing the risk of coolant leaks. In the unlikely event the heat exchangers cannot remove heat, the VTR design includes an independent system that operates entirely upon laws of gravity and buoyancy, called the Reactor Vessel Auxiliary Cooling System, or RVACS. A practical analogy to describe how RVACS works is your home fireplace. After all the wood or fuel has burned, the coals that remain continue to produce heat, which escapes safely through the chimney. A nuclear reactor is similar. After the reactor shuts down, the fuel in its core continues to produce residual heat, called decay heat, that needs to be removed. In the VTR, the RVACs would function like the chimney and remove this decay heat. Even if power to the sodium-to-air heat exchangers is lost, the RVACs removes heat normally and naturally without need of human intervention, electric power, or equipment manipulation, thus increasing reactor safety. The VTR design also incorporates mechanisms and barriers to control the location of radioactive materials within the reactor core and facility. During operation, radioactive fission products are produced in the reactor fuel, which is contained in a metallic tube called cladding. The operating parameters allow for robust protection and large temperature margins to cladding failure. In the rare case that fuel cladding fails, the sodium coolant would absorb the fission products. Ultimately, the reactor vessel, coolant cover gas cleanup system boundaries, and the reactor containment boundary provide a significant number of safety barriers and defensive layers. Support facilities, including the control room and vital systems such as switchgear and control system components, security, office support, and utilities like electric, will be included. The requirements for the proposed VTR are based on input and recommendations from industry partners and other potential end users. To meet these requirements, the VTR will leverage existing U.S. government and industry investments in nuclear reactors to accelerate the design and construction process, using proven nuclear reactor technology to enable world-class scientific capability.